where you'll find a lot of valuable content, such as recent research articles and job opportunities, for example. As always, you can ask your questions for today's lecture using the lecture Q&A channel on the CCAI community platform. If you check the CCAI website and go to Summer School 2023 page, you'll find a direct link to the comment section as well. We'll do our best to ask as many questions as possible, but given the high number of participants, maybe not all questions will be asked, but questions with more upvotes will get a higher chance of being asked. So be sure to upvote the questions you find most interesting. And very importantly, all participants are required to abide by CCAI's Code of Conduct. If any situation should arise, please report to reporting@climatechange.ai. In the schedule for day 11, we'll have a lecture on AI for human and social systems by Hannah Druckenmiller. So it's my pleasure to open the session and introduce our speaker. Dr. Hannah Druckenmiller received her PhD in agricultural and resource economics in 2021 from UC Berkeley. She is an assistant professor of economics at Caltech, an affiliate of the Center for Science, Society, and Public Policy, also at Caltech, an university fellow at Resources for the Future, and a William H. Hurt Scholar. Her research is focused on environmental benefits and economic costs associated with natural resource protection. Hannah, please receive our warmest welcome, and the floor is yours.
Thanks so much, Amanda.
Just stop sharing my screen. Just a second. I seem to have lost. Yeah, okay.
All right, all set. Well, thank you so much to the whole team at Climate Change AI for inviting me to be part of this lecture series. I'm really excited to be here. As Amanda mentioned, my name is Hannah Druckenmiller, and I'm an assistant professor of economics at Caltech. I work mainly on the social and economic costs of climate change, and I'm increasingly finding myself using machine learning and AI in my own research. So I'm really excited to be here with this group and engage on this topic today. I'm going to start by providing an overview of the impact of climate change on human and social systems. This is way more than I could cover in a full 2-hour lecture, so it's going to be very high level. And I'm going to hopefully provide you with an overview of some of the tools that economists like myself use to study the social and economic impacts of climate change so that you can begin to see where AI might fit in here. Then I'm going to go over why I think AI is very well suited to addressing some of the challenges associated with climate adaptation and mitigation related to human and social systems. I'll provide some brief examples of climate applications in this area to get the juices flowing. And then I'm going to do a deep dive into 4 specific tools to just give you a preview of the types of tools that folks are using in this area. Some of these examples are going to focus on tools that academics like myself has developed. Others are going to focus on tools that practitioners and investors are using in this space. So let me just start by motivating why researchers care about the impact of climate change on human and social systems. This is a question that's been floating around for centuries. To what extent does climate shape society and human well-being? We've seen questions like, are climatic differences between countries at least partly responsible for differences in economics, politics, and culture? So how much does climate shape the wealth of nations? We've also seen questions for centuries whether large-scale social transformations are triggered by changes in the climate. But questions like this have received renewed attention in the last couple of decades as society has become increasingly concerned about anthropogenic climate change. And now there's a wealth of research that takes quantitative approaches to tackling these questions using a mix of data and methods from climate sciences, social sciences, statistics, and many other disciplines. For those of you that are interested in kind of an overview of this field, I'm going to point you towards the article at the bottom cited here by Tama Carlton and Sol Xiong that was published in Science back in 2016. And although some of the literature that they review in this article is a little outdated at this point, because this is a fast-moving field, it provides a great framework for thinking about how we can make linkages between the climate and social systems. So one of the main reasons that policymakers and that people around the world care about climate change is that we think it's really going to impact human systems. And one of the things we're most concerned about is that it's going to impact economic performance or productivity. And so I'm going to provide, before we get started on the full lecture, an overview of the types of tools that economists use to understand the linkages between climate and economic output. One of the main sets of tools is called integrated assessment models. And these are basically big theoretical numerical models that link human and social systems with the environment. They try to model feedback so that you can feed in a set of assumptions about what we think is going to happen in social systems, what we think is going to happen in the environment. And then all of those interactions are modeled so we get outputs of projections about how climate change is going to impact human well-being. These models rely on damage functions. For those of you who haven't heard this term before, this is basically a function that relates changes in climatic conditions to changes in human well-being. So we could look at changes in economic output, we could look at changes in human health and mortality, we could look at changes in energy use. The damage function is what's going to translate those changes into climate into changes in outcomes that we care about. For the early literature in the 90s and early 2000s, these damage functions were largely assumed. So we might assume, say, a quadratic response between a climate variable like temperature and an outcome we care about like health. Increasingly, however, these damage functions are recovered from the data, meaning that we're using statistical methods to actually map the relationship between climate and well-being. And that's going to be one of the focuses of the lecture today. So let me just start by giving an overview of IAMs, or integrated assessment models. This is a very simplified picture of how these models work. So the researcher is going to make some assumptions here on the left-hand side about changes in the global system. So these include assumptions about how the economy is going to grow over time, how population is going to change over time, and the policies that different countries are implementing to stimulate growth and to regulate their environment. There's a whole other slew of assumptions that also get baked into these models. The model describes the linkages between the economy, the climate, and other things we care about, like land and energy systems. And then when you run your set of assumptions through, you get a set of outputs that describes the impact of climate change on economic outcomes. We also get emissions pathways, energy pathways, and projections of land use. The goal of these models is to help inform decision-making today by understanding how it's going to affect future outcomes. Now, I just showed you this very simplified picture of how these models work, but in practice, they look more like this. These are very complex, and they require a myriad of different assumptions. So increasingly, and so the goal of these things is to give us an understanding of how climate change might impact the economy. And so this is what the output of an IMA might look like. You can see on the x-axis of this main graph, the economic impacts of future climate change in trillions of US dollars. And then on the y-axis, we have a number of different scenarios. We call them shared socioeconomic pathways that basically bake in a number of different assumptions about how population, the economy are going to evolve. So for example, the top row here in green is a sustainable pathway where we're seeing low levels of population growth and emissions. And under this pathway, we expect relatively modest impacts of climate change on the economy. If we move to scenarios 3, 4, or 5, these are higher population growth, higher emission scenarios, and we would expect more negative impacts of climate change on the economy because we're seeing larger temperature increases and feedbacks between the climate system and the economy. So, like I mentioned, in the early years, these models were based primarily on assumptions, and where researchers are today is trying to make these models increasingly data-driven. And this is where I think AI has a really important role to play. And so I'm going to focus a little bit more on how data enters into modeling these days. So like I mentioned, these models rely critically on something called damage functions, which maps the relationship between climate and social outcomes. And so I'm going to give you a walkthrough here of how that mapping is done. So you can imagine climate as a probability distribution over different weather events. Here I'm showing you on the slide 2 different probability distributions of climate. On the left-hand side, we have the blue climate, where we might see, say, a lower mean temperature with less variability. And then on the right side, we see a shift in climate to this pink climate, where we might have a higher mean temperature with increased variability. Each of these climates is associated with realizations of weather events. So these are things like temperature that you experience on a daily basis or precipitation that you experience on a daily basis. And the types of realizations that we see depend on the climate distribution that we have. Now, each of these weather realizations can be mapped onto a social outcome variable. For simplicity, let's just assume that income is here on the y-axis. And so what this is, it's a dose response function, or I called it a damage function earlier, is it's describing the linkage between a weather realization and the social outcome that you care about. So say you have a 1 degree increase in temperature, we might expect a 1% increase in human mortality. That's what a dose response function would tell you. Now, dose response functions can change as populations adapt to different climates. So in this simple diagram here, the blue dose response function is for a population that has that lower mean temperature climate. If the climate shifts in the long run, you might expect that people become less sensitive to temperature. And so the dose response function is going to shift out to the right. Then what we can do is we can map these weather realizations through that dose response function to get our expected social and economic outcomes. And if we do this for 2 different climate scenarios, we can get the probability distribution of different social and economic outcomes under different climate realizations. So to fix ideas, imagine that our climate today is the one with the blue probability distribution. Our climate in 2100 is the one with the pink probability distribution. We can map this through the dose response functions that we estimate using statistical techniques, and that gives us our expected distributions of social and economic outcomes. And so when you hear numbers like climate change is expected to reduce GDP by, say, 10%, that's a central estimate, but it's masking a lot of uncertainty in how climate might affect the economy or might affect society. And so that's why we like to think of these as distributions rather than just one number. Okay, so hopefully that made sense about how we map climate realizations into social and economic outcomes. Now I want to provide you with a couple examples of how researchers have done this to be able to understand how climate change might impact society moving forward. So here's an example that resembles closely the process I just described, where researchers related changes in temperature to changes in economic output as measured by GDP, which stands for gross domestic product. This is kind of a measure that we use to summarize economic activity. It doesn't include all dimensions of human well-being, but it's something that's well recorded across the globe. And so it's important to be able to understand how it might evolve with changes in the climate. And so what these researchers did is they looked in the past at how changes in temperature have affected growth rates for GDP across all nations globally. And then they tried to map out a relationship between temperature and economic output. And what they found is this kind of inverse U sign graph that I've plotted here on the left, where at low temperatures, we see negative effects on growth rates. And at high temperatures, we see negative effects on growth rates. And kind of the ideal temperature for economic growth is somewhere around 10 to 15 degrees Celsius. So it so happens that many of the large economies today are located right around this, what we call bliss point, where they're at a level of temperature that's associated with kind of optimal economic output. If these countries experience increases in temperature under climate change, we can expect them to move down this curve, so they'll have negative impacts on their economies. Some of these countries in Northern Europe, like Germany, the UK, and France, are located below the optimal point. This suggests that with increases in temperature under climate change, they could actually see beneficial impacts on their economy. And unfortunately, many of the largest population countries that are also tend to be lower income are located high up on this response curve, meaning that they've already seen negative impacts of climate on their economy. And as climate warms, growth rates are expected to be impacted pretty steeply. So this type of estimate is how you get maps like these that project the impacts of climate change on the economies of different countries. And this might be a pattern that folks on this call are familiar with, where we're actually expecting to see benefits of climate change in some areas of the globe, here highlighted in blue. So these are areas like Canada, Russia, Northern Europe, where temperature increases could actually be beneficial for economic productivity. But most of the world is expected to see negative impacts of climate change on their economies. And this problem is particularly bad in countries that are high population and that are low income today, like much of sub-Saharan Africa, South Asia, and Latin America. So that's one study that looked at the impact of climate change on GDP, but there's many other dimensions of human well-being that we care about that are not necessarily captured in GDP. For example, GDP doesn't capture impacts of climate change on health or human mortality, on conflict or migration, or arguably on labor productivity. And so there's actually a whole range of studies that are looking specifically at these sectors using similar techniques to the ones that I just described. I'm going to show you one on health for illustrative purposes, but you can imagine doing this on your sector of choice. So there's a lot going on in this graph, but essentially this paper tried to do the same thing, but instead of looking at GDP as the outcome, they're looking at human mortality as the outcome and modeling it as affected by temperature, precipitation, and other climatic conditions. If you focus first on the graph on the lower left-hand side here, this is the type of response function that you saw for GDP, where there are negative impacts of temperature at low temperatures on health. So when it's really cold, people experience more mortality. When it's really hot up here around 35 degrees, people experience mortality. And the ideal temperature is somewhere in the range of what we saw previously, around 15 degrees Celsius. Now, why are there 9 plots on this slide? Well, this paper didn't just model one relationship globally. They actually looked at how this relationship between the climate and their outcome of interest, health, differed by 2 dimensions. So the first dimension was your underlying climate, which is here in the columns. So the leftmost column is places that began with cold climates. You could think of Norway. The middle column is temperate climates, think the United States. And the third column is hot climates, think India. They also did this by income. So the top row is high income countries, the middle row is middle income countries, and the bottom row is low income countries. And kind of the punchline of this graph is that low income cold countries are very sensitive to temperature because they have limited capacity to adapt to it. They haven't had much experience with high temperatures. These are cold places. So they haven't made many investments in protective infrastructure like air conditioning that allows them to deal with high temperatures. They're also low income, so they've made less of those investments for capacity reasons. But if we move from these cold places to hotter places, we see kind of a flattening of this curve. So people become less sensitive to high temperatures. As you might expect, they actually become more sensitive to cold temperatures because, like before, they're less used to dealing with these conditions and so less well adapted to them. We see a similar pattern when we move from low-income countries to high-income countries, where high-income countries are less sensitive to climate extremes than low-income countries. So the good news here is that the relationships that we trace out today between climate and human well-being are actually probably going to be tempered in the future as global GDP grows, so as the world becomes richer, and as the climate changes, so as people get more experience dealing with these climate conditions that they're not used to today. So using kind of these heterogeneous or differential responses across space, this study was able to make this map of the health impacts of climate change across the globe. And you'll see similar patterns here where we actually see some benefits of climate change on health in blue here in high latitude places and kind of significant damages in low latitude low-income places. So hopefully now I've convinced you that we're expecting impacts of climate change on both the economy and on dimensions of human well-being like health that are not directly measurable through income statistics like GDP. And this is increasingly becoming a data-driven exercise where relating changes in climate to changes in human well-being is able to help us project the future impacts of climate change. I'm going to skip this because it's somewhat similar, but I just showed you an example on health. You can imagine similar studies that are done in other sectors. This one was done in energy use. And so if you add up all of these different impacts across different human and social systems, you're able to arrive at kind of an overall impact of the damages of climate change. Now, why is that number useful? In addition to just being intellectually interesting, we really care about the damages from climate change because they allow us to decide the optimal level of intervention by the government. So if damages from climate change are expected to be very high, that's big incentive for policymakers to step in and do something to curb emissions. If damages are expected to be relatively low, maybe it's better to let the economy play out so that we don't curb economic growth and hurt society in other ways. The way that we make the decision of exactly how much the government should intervene is through something that we call the social cost of carbon, or the SCC. So put simply, the social cost of carbon is an estimate of the economic damages that would result from emitting 1 additional ton of carbon dioxide into the atmosphere. Now, the goal of this statistic is to put the effects of climate change into dollar signs so that they can be directly compared with the cost of mitigating climate change, of curbing CO2 emissions. At risk of belaboring this point, I'm going to play a brief video on the social cost of carbon that explains this concept, because I think it's really important to understanding why policymakers intervene and how data can help us decide the right level of intervention.
Greenhouse gases in the atmosphere affect the climate, the economy, and people's well-being. The social cost of carbon is an estimate in dollars of the economic damages that result from each additional ton of greenhouse gas emissions. It puts the effects of climate change into economic terms to help policymakers understand how emissions-related policies affect the economy. For policies that affect greenhouse gas emissions, the expected increase or decrease in emissions in tons is multiplied by the social cost of carbon, and the result is included as part of the total estimated costs or benefits of the policy. Let's look at an example. A city government official is evaluating a policy that would expand their city's public transit system. To make an informed decision on whether or not to implement the policy, policymakers often evaluate and sum all of the costs and benefits that will accrue each year into the future. Let's start by looking at the costs and benefits in just the first year of the policy. The total infrastructure costs in the first year are estimated to be $50 million. The benefits in the first year are estimated to include $5 million in revenue from increased ridership and $10 million in health benefits from decreased local air pollution and increased walking. In order to calculate the policy's climate benefits in a given year, we need to multiply the reduction in CO2 emissions by the social cost of carbon. This policy will reduce carbon dioxide emissions by an estimated 100,000 metric tons of CO2 per year. If, for example, the social cost of carbon is estimated as $50 per metric ton, then the benefits from avoided climate damages would equal $5 million in the first year. Looking at just the first year of the policy, the $50 million of costs exceed the benefits, which add up to $20 million. For a full benefit cost analysis, however, the government official would continue adding up the ongoing costs and benefits for a number of years into the future. Because infrastructure costs primarily occur in the first few years and benefits from emissions reductions will continue each year into the future, the total benefits from the project may outweigh the total cost of the project in just a few years. Without the social cost of carbon to account for the climate benefits of policies, the ongoing benefits of avoided climate change might be missed in policy analysis assessing other costs and benefits. The social cost of carbon is used around the world to inform billions of dollars of policy and investment decisions. The federal government has used it in analysis of over 150 proposed and final regulations. States like New York, Illinois, Colorado, Minnesota, Washington, and California use the social cost of carbon for policy analysis or implementation. The Canadian government has adopted the estimation methodology. Federal carbon tax proposals have suggested a starting tax level based on the social cost of carbon. RFF is engaged in an effort to improve the scientific basis.
Okay, so hopefully now that provides some context for the social cost of carbon and why it's useful for decision makers. But one frustrating thing about the social cost of carbon is that it's very hard to pin down, okay? So here you're seeing a distribution of estimates of the social cost of carbon under different assumptions. One thing that really affects what we think the social cost of carbon is how much we value future well-being. We do that using a discount rate, called a discount rate. So a higher discount rate means you put less weight on future generations' well-being relative to today. A lower discount rate means you put more weight on future generations' well-being. And so you can see in the colors here that the social cost of carbon is very sensitive to this discount rate, but it's also, we see a wide range of it even within a discount rate. And those ranges come from different assumptions about the climate scenario, population, GDP growth, all of these things that are baked into our models about the linkages between climate and the economy. So this is an area where we really need better data and models to be able to pin down the social cost of carbon so that we can make more informed decisions about when it's worth regulating the climate and when it's not. So before I move on, to kind of examples of how AI can help in these areas that I've just talked about, I wanted to just throw out what I think are some of the big open questions in climate mitigation and adaptation as it relates to human and social systems. So when I say mitigation, I'm talking about how we can reduce CO2 emissions to reduce the impacts of climate change in the future. When I say adaptation, I'm talking about how we can make society more resilient to climate changes, assuming that they are going to occur since we already have CO2 building up in the atmosphere. So as you might have guessed, one of the big open questions, at least in my opinion, is what is the social cost of carbon? There are also a number of other big climate mitigation questions related to what are the different pathways towards a net zero economy, net zero meaning zero emissions when you take into account all of the sources and sinks, and which of these approaches are actually politically feasible and cost effective. In the realm of adaptation, there's lots of questions about which adaptation measures are most cost effective. But there's also a whole set of questions about adaptation measures that we know should save people money, but people don't appear to uptake on their own. So I might tell you that you could really reduce the flood risk of your house by elevating it a foot off the ground. This is going to cost you $10,000, and I'm guessing it's going to save you $50,000 in the long run. We don't see people taking up these investments that should actually save them lots of money. And a big question is why? And another set of questions around adaptation is what are the unintended consequences of some adaptation practices and policies? So to return to the flooding example, one of the big adaptation measures that localities take to prevent flood damages is building something called a levee, which is basically a physical barrier between water and exposed capital like buildings. Levees have been promoted as a way to adapt to climate change, but recent hydrological modeling has shown that while they do a good job of protecting local buildings, they actually displace floodwaters and can increase damages downstream. These are the types of things that we need more data and models to be able to better understand how they're going to play out in the real world. Okay, so hopefully now I've set the stage of kind of some of the big questions in climate mitigation and adaptation, at least in this sector. And so next I want to provide a very high-level overview of why I think AI is well suited to addressing many of these challenges. The first, like you might have guessed from listening to the introduction, is that prediction is really central to understanding the social risks posed by climate change. In order to calculate the social cost of carbon, for example, we need to be able to predict changes in the climate system, changes in human systems like population growth and changes in wealth, and how society is going to respond to climate change. Now, of course, machine learning and AI are great at prediction. So this is an area where these methods can really enter into the existing framework. The second is optimization is going to be really central here. Optimization allows us to allocate scarce resources in the most efficient way possible. And climate change is all about resource allocation, especially when it comes to targeting adaptation investments. We have way more ideas of how we can adapt to climate change than we have resources that allow us to do so. And so being able to optimize, especially across multiple dimensions, is really first order here. And then the final way is that AI is really great at dimensionality reduction. It helps us ingest enormous amounts of data and make sense out of it. And climate and human and social systems are an area where we have more data than we know what to do with. We have measures of temperature, for example, that are taken every millisecond all across the globe. And we have measures of social outcomes like energy use that are taken at equally high frequency. Being able to then link changes in climate to changes in those social outcomes like energy use is hard to do without dimensionality reduction that AI offers. Lastly, I'm going to steal an idea of how AI could help from one of my favorite blogs, which is the Energy Institute blog out of UC Berkeley. And this blog was titled, "Can ChatGPT Save the Planet?" But one part of it that I thought was really interesting was talking about how AI could aid in climate innovation. And basically what Jim does in the blog is he outlines that lots of research in economics shows that innovation globally has been slowing down. But in the last couple of years, we've seen this kind of really huge leap in AI that potentially holds the possibility of reversing that trend. And the reason that this is encouraging for climate change is that we need innovation, not just in technology that's going to allow us to mitigate climate change, but also in policy and governance systems, in economics, in marketing and communication systems that can change behavior in order to tackle this challenge. And so AI as a disruptor could offer one way to really kickstart innovation across a wide range of sectors. It's worth pointing out that AI is not just useful for one stakeholder group here, right? I've given you a couple examples of how it's helpful to researchers, partly because I am a researcher, but it also is very helpful to investors, businesses, governments, because it allows us to do things like predict financial risk and optimize investments. It allows us to identify efficiency gains and cost savings for businesses. And it allows us to improve adaptation planning, disaster response, and public service provision. These hit across a wide range of stakeholders, and hopefully the examples that I'm about to provide will help drive this point home. But while AI offers many opportunities across a wide range of stakeholder groups, it's also important to recognize that it's by no means a silver bullet. And in fact, AI can actually introduce additional challenges that we should all be aware of as people who are interested in this space. I'm going to point out, a couple of thoughts here, but there's many other points to be made under this topic, and hopefully we'll be able to enter into some of them in our discussion. But one thing that's really interesting about AI is that it's great for some types of tasks like prediction, which we've talked about, but it can also be misused for others, like causal inference. Causal inference is the science that allows you to link a change in, say, policy with a change in an outcome on the ground. And it's really important for anticipating the consequences of our actions. But AI is not always the best suited to recovering causal effects. It's better suited to recovering associations between two variables. The other thing to note about AI is that it's an information provider, first and foremost. And information can be very helpful in guiding decision-making, but ultimately it's still up to people, it's up to governments to actually enact change. And so this isn't somewhere where we can just sit back and hope that technology fixes the problem for us. And I'd be remiss to not mention that while AI offers a lot of promise for climate mitigation and adaptation, it can also pose additional challenges. So you may have seen in other lectures throughout this series that AI can really lower the cost of production of many different things, of energy production, of running buildings and cities. And while those increases in efficiency can be associated with reductions in emissions, they can actually also be associated with increases in emissions if lowering the cost of production makes production more worthwhile for firms or investors. Finally, this is another point from that great blog that I shared on the last slide. AI could pose an additional challenge if it disrupts industries in a way that displaces workers and increases social division. One thing that we really need for climate progress is unprecedented global cooperation, and that is difficult if we're dealing with other social challenges that are caused by AI disrupting the economy and social systems. Okay, so let's move on to some concrete examples of how AI can actually help in climate mitigation and adaptation. I'm going to start with a short list of kind of examples that I find interesting. I'd like to note that these are not meant to be exhaustive, but rather to give you a flavor for some of the way that AI can help address the climate challenge. So some of the things that I'll talk about are better understanding the impacts of climate change. So in the back of your head, think social cost of carbon, better targeting adaptation investments, predicting climate crises and issuing early warnings so that we can limit social damages. And one of those in particular is anticipating food insecurity and being able to respond to it in a way that minimizes human suffering. Okay, so let's take a step back and return to the social cost of carbon and pay attention here, because after we go over how the social cost of carbon is calculated, I'm going to ask you how AI could be useful in producing the better estimates of the social cost of carbon to hopefully spark a discussion on this topic. Okay, so the social cost of carbon is calculated in 4 broad steps using those integrated assessment models that I introduced at the beginning of the lecture. The first step is that you need to predict future CO2 emissions based on population, economic growth, the energy mix, and many other factors. The second step is you model the climate response to a change in CO2. So by climate response, I mean changes in climate variables like temperature, precipitation, sea level rise, and so on. The third step is to assess the economic impact of these changes on many different sectors of the economy. For example, agriculture, health, energy use, and so on. And finally, you're going to convert those damages into their present day value and add them all up to determine the total damages. So you got a preview of that in the social cost of carbon explainer video, where it's not just damages today that we care about, but all of the damages in the future that are going to be racked up because of a change in climate that we cause today. Okay, so now I'm going to take a second and open this up to an open-ended audience poll on how AI could be useful in producing better estimates of the social cost of carbon. Amanda, do I need to do anything? Okay, awesome. So hopefully you all are seeing that poll appear on your screen, and I'll give you a few seconds to respond to it with just the reminder that there's these kind of 4 steps where data and methods could help us improve the social cost of carbon, which is predicting future emissions, modeling climate responses, assessing the economic impacts, and then converting those future damages back into their present day value.
We have no responses yet, and there's a little bit of delay in the live stream. So yeah, if we could continue a little bit, we can go back to that.
So while we wait for those responses to trickle in, I'll just talk about a couple of their areas where I think AI can be helpful in better understanding the impacts of climate change on society. One that we previewed earlier is that climate impacts are not uniform across the whole global population. There's a lot of differences in how different populations respond to the same change in climate. And here is an area where we really need better models to understand what's driving these differences. So the state of the art here is what I showed you earlier, where we look at differences in these responses by summary statistics like income or like underlying climate in bins like cold, medium, and hot. But the kind of differential responses are most likely much more complex than that, right? It's not just whether you live in a cold or a hot place, but it's all of these dimensions of your society that determine how sensitive you personally are to a change in the climate. And so this is an area where we really need better models and data to be able to understand these differential responses. And there's lots of exciting work on how AI can be used to model heterogeneity and treatment effects that I think we could really bring to bear in this literature. A second kind of exciting area where AI can improve our understanding of the impacts of climate change is being able to attribute damages from climate change to specific polluters. Now, why might you want to do that? Well, first of all, if you're able to see which specific polluters are causing the most damages, you can target policy interventions to have the greatest impact. So you can target those really damaging polluters and make sure you're curbing their emissions first. The second reason that this might be useful for climate policy is that kind of at a high level, an idea has been floated out there that the people or firms that are causing climate damages should be responsible for financial transfers to those people who are suffering the damages from their actions. And we can't actually ever make that type of financial transfer between the people who are causing the damage and who are suffering the damage without knowing the source of the damage. So these are two good reasons why we might want to be able to attribute damages from climate change to a specific polluter. There's a really interesting application called Climate Trace that is doing exactly this. And they're using AI combined with satellite observations to be able to provide a very detailed emissions inventory across the globe. And so you can imagine seeing, a satellite observation of, say, CO2, and using artificial intelligence to be able to trace back that CO2 to the specific polluting firm or industry. And Climate Trace does this, and it has compiled the largest inventory ever of CO2 emissions that's able to trace the emissions of over 80,000 sources. So this is kind of one exciting application in the climate impact space. All right, Amanda, have we gotten any responses on the poll yet?
Yes, we've got 9. They're still coming in, but I can share my screen right now. There you go.
All right. So prediction and modeling steps seem likely to be supported by AI. Awesome. So like we talked about, AI is great at prediction. So things like predicting population growth at a very granular level, so not just by country, but by municipality or even township. Will really help us understand the assumptions that get baked into these models. Handling high dimensional and multidimensional data sets. Exactly. So here the audience member says, text satellite images. So we just saw an example of how satellite data on pollution could be used to understand climate impacts. I'm going to show an example later in the talk where text actually becomes very important for predicting vulnerability to climate impacts. Incorporating more data from various sources. Exactly. So AI is really great for being able to model complex interactions between different factors. So we can see, models that allow for highly nonlinear relationships between, say, population, income, underlying climate, when you're thinking about heterogeneous damages across space. Optimizing resource and budget to improve city services and reduce waste. Great, we're going to see some examples of that later on. Giving us a better idea of which parties are responsible and litigating against them. Okay, so that's right on line with what we've seen. So I'll allow you guys to continue to kind of ponder this question, but I think kind of the point here is that there's multiple steps along this framework of understanding how climate impacts society that could really be improved by AI that is both as a data provider. So AI allows us to produce granular data sets of, say, pollution or well-being from data sources like satellite imagery or aerosol optical depth that we're just not able to collect using traditional methods. And as a modeling tool to understand complex interactions between these many different factors that shape the response between climate and human well-being.
Can I stop sharing?
Yep, I'll take back over. Okay. Okay, so another area where I think AI can be especially useful is targeting adaptation investments. So we have limited budgets globally to be able to invest in resilience and adaptation to climate change. I think we saw a couple of responses in the last response that were kind of targeted at this question, but instead of doing the audience poll again, since there is this time lag, I'm just going to move on and give a couple examples of how I think AI can help target adaptation investments, and then we'll talk about some specific applications of AI for predicting and anticipating crises. So one way is that we can use AI to optimize resource distribution. This is under the constraint of a fixed budget, so we can't invest in everything that we think would be helpful. And where I think AI could be particularly useful here is allowing us to account for complex interactions between different adaptation strategies. So not each adaptation strategy doesn't happen in a vacuum. Investing in one strategy over here could either increase or decrease the utility of investing in a second adaptation strategy over here. And so being able to map out those complex interactions is really helpful for allowing us to optimize investments, given that we don't have unlimited resources. The second is identifying and projecting the consequences of adaptation investments that might have very complex interactions. So before I gave the example of flood levees being something that we originally thought was quite a good investment in adaptation because they protect structures from floodwaters. But after advancements in hydrological modeling, many of which use artificial intelligence, we were actually able to identify that levees increase damages downstream. And so they need to be very carefully placed to maximize the amount of structures that they're protecting and minimize the amount of structures that they're actually exposing to increased risk. So again, hopefully you can see that there's a role for AI to play here. Okay. Another area that AI can be really helpful for is predicting crises that are exacerbated by climate change and helping us issue warnings in a timely manner. So one thing that AI is good for is ingesting vast amounts of data quickly and making predictions in a timely manner so that they're actually actionable. We don't want to know about a flood after it's happened. We need to know with enough lead time for people to actually evacuate and for emergency aid to be distributed in a way that saves lives and prevents damage to property. So one area where AI is already at work here is predicting natural disasters like floods and wildfire progression, and using those predictions to issue early warnings, to target suppression efforts for wildfire, and to target humanitarian aid for floods. So I'm going to show one more video that gives an example of AI for wildfire prediction that I think is a really nice application.
The East Troublesome Fire started on October 14th, 2020, northeast of Kremlin, Colorado. Low overnight humidity and high wind gusts primed the area for fast wildfire conditions. Within 9 days, it had burned nearly 200,000 acres and reached the east side of the Continental Divide. The East Troublesome Fire is an especially notable case study for Colorado because it spread nearly 87,000 acres in just one 24-hour period. Wildfire forecast models give us estimates of fire spread that can help inform active fire response and evacuations. But these models rely on accurate information, and until now, we've lacked up-to-date vegetation data. In fire science language, we call this fuel data. The ways we've traditionally collected fuel data can be labor-intensive, and compiling and verifying them can take a long time. Although the fuel data are published as frequently as these methods have allowed, they are easily outpaced by events like flooding and drought that dramatically change the characteristics of fuels in an area, and subsequently the accuracy of the fuel data itself. At the time of the East Troublesome Fire, the only available fuel data showed the trees as healthy and standing. If we were to model fire in a healthy forest, like the available fuel data represented, the trees would hold more moisture, and their upright position makes them more challenging to ignite. However, a lot of the forest was actually dead and downed due to drought, beetle infestation, and wind events that occurred since the last fuel data had been published. Dead, downed trees tend to hold less moisture, and their positioning on the ground makes them more accessible to ignition. If we model the East Troublesome Fire using updated fuel data that captures the dead, downed trees, the fire moves more quickly, and we have a better representation of what actually happened. To help fill the gap in data, we can now update the fuel data using satellite imagery. The satellite imagery is able to tell us where the vegetation is green and healthy and where it's brown and dry. It can also tell us where the most beetle-infested areas are, where the trees are lying on the ground, and where they're still standing, and funnels it into categories of severity that are simple for the model to digest. Wildfires are a natural ecological process that will continue to occur, but with more accurate information, our ability to save lives and property can be dramatically improved. If we can predict with greater certainty, we can act with better tools and strategies in hand.
Okay, so that was one example of how AI can not only help us fill data gaps that allow for better models, but actually improve predictions themselves. And kind of the goal here is that natural disasters like wildfires, like floods, like disease outbreaks are expected to become more common with climate change, and we're going to need better methods for anticipating them and reacting to them if we're going to stave off some of the worst impacts. Another area where this is true is disease surveillance. So disease surveillance and outbreak forecasting can really help in containment efforts. If we know early that an area is at risk of an outbreak, we can implement measures like isolating or social distancing that allow for slower spread of the disease. I think many of us are all too familiar with these techniques after COVID. Unfortunately, climate change is expected to increase the incidence of many diseases, especially vector-borne diseases like malaria. And so one goal for mitigating some of the worst impacts of climate change is to be able to better anticipate these disease outbreaks and respond to them before they become unmanageable. I think this is a really neat AI application, which is to change early detection of malaria. So For some background, traditionally, malaria is detected using optical microscopy examinations of blood smears. So this is something that needs to be done in a lab by a technician, and it's both time-consuming and extremely expensive, which makes this very hard to do in low-income countries with limited capacity. However, increasingly, we're finding that AI systems like convolutional neural networks can actually emulate this microscopy visualization of an expert with decent accuracy, but at much greater speed and lower cost. And in fact, some studies are suggesting that you could actually do this by just taking a picture of the blood smear on your smartphone and uploading it to an app that did the inspection of the smear for you using a convolutional neural network. So this is far from being implementable in practice. There's a lot of work left to be done here before real world usage is possible. But these are the types of solutions that are being developed and that are out there to help increase response times in the face of increasing crisis under climate change. Another category of climate risks that relates to human and social systems is the threat of increasing food insecurity. So food insecurity is also already a massive global problem, but it's expected to become worse as climate variability increases. And accurately predicting when and where hunger crises will occur is thought of as very critical to an effective humanitarian aid response. Today, the state of the world is that food insecurity predictions largely rely on expert opinions. There's some traditional models that input data on, for example, food prices and weather to predict food insecurity. But modeling is limited by the amount of data that's available, especially in resource-constrained settings, like the low-income countries that are most often affected by these crises. So AI offers one pathway towards ingesting large amounts of data from different non-traditional sources to come up with projections of where food insecurity might be worst so that we can respond to this in a timely manner. Current state-of-the-art models have accuracies in the range of, say, 60 to 80%. I'm going to show you one in our deep dive that seems particularly promising and that uses text analysis. So it's kind of pushing the boundaries of state-of-the-art here. Another way that we could improve food security outcomes besides predicting crises is thinking about ways to reduce food waste. So it's currently estimated that about a third of global food that's produced and intended for human consumption every year is wasted. So it either spoils or it is thrown out, but it doesn't actually reach the mouths of people who need it. This is a massive amount of food, both in volume and value. And it's estimated that it's enough to feed about 3 billion people. So you might have heard that there is enough food out there to feed the whole world. We're just not able to allocate it in a way that solves global hunger. Part of this is because we're wasting a large portion of the food supply, which not only increases food prices and increases hunger, but it also takes a toll on our environment. For example, it's estimated that food waste ends up wasting about a quarter of our global freshwater supply in uneaten food. I'm not sure whether this was covered in previous lectures, but AI really offers a few different pathways for reducing food waste. One is that the production, shipment, and climate-controlled warehousing of food products that are perishable is a major source of greenhouse gas emissions and of food waste. And so being able to better predict where food is needed and where it's going to be wasted is one possible way to reduce these demands on both the food system and the climate system. Okay, so hopefully we have a flavor now for the ways that AI can help in human and social systems. Now I want to do a deep dive into 4 tools to give you a much more hands-on idea of how practitioners and researchers in this space are using AI in their work. Before I do so, we're at the hour mark, so I just wanted to pause for a second and ask our lead TA, Amanda, if there's any questions that she thinks now is a good time to surface.
Yes, we do have a couple of questions. So, for example, could AI help to identify clusters or characteristics of populations where emissions are greatest, or where adaptation needs are greatest?
Yeah, so I think that this is a really great point, which is for clusters where emissions are greatest, this is basically what this exercise is trying to do. It's very hard to trace back emissions to their exact source, especially for sources that aren't monitored by regulators. So you can think of, electricity generators or people with smokestacks as emissions that we can easily observe, but there's many other types of emissions that are dispersed across space and that are much harder to observe. Like say applying fertilizer to your land, this is kind of non-point source pollution that we don't have any record of in survey data, but that perhaps AI can help us trace back to the sources to be able to better target policy interventions. And the other point is really related to this about where are people most vulnerable to climate change so that we can target adaptation investments towards these areas. If we're able to unpack in a data-driven way what makes populations particularly sensitive to changes in their climate, it will allow us to better target interventions that might help those populations that have the highest level of vulnerability to adapt, either by directing resources towards them or towards directing information interventions that help people understand how other populations have adapted to make themselves more resilient.
Thank you. There is another question that is perhaps a bit related to the same subject, but more specific. Could we also measure the degree of impact on social minorities, for example, single mothers, LGBTQA+, and refugees?
Yeah, so I think the goal would be able to understand the impacts at this very granular level, even to the extent of kind of coming up with individual level predictions of how much people will be impacted by climate change. It's really hard when you're dealing with data that's messy and trying to trace out these causal relationships. And so far, kind of researchers have focused on these big dimensions of heterogeneity, like income or underlying climate, to help summarize these impacts. But as the data gets better and as the tools get better, I think the goal is to do exactly that. It's to be able to trace out specific segments of the population that are especially vulnerable so that they can receive attention by policymakers in terms of directed resources.
Also, if I could circle back on another point, if you could just clarify why in the beginning of your lecture, you mentioned GDP and not Human Development Index. Could you please explain more about that?
Yeah, so for those of the listeners that aren't familiar with Human Development Index, that is an alternative measure to measure human well-being. GDP or income measures it in dollar signs. The Human Development Index takes into account three dimensions of the population's well-being. So income, but also human capital. So you can think of that as knowledge and health. And it's thought of as a kind of more comprehensive measure of human well-being. I think the main problem here is just data constraints. We have really good data on GDP at the subnational level, so below country level, going back to the 1970s in many locations. So that gives us a long time span in which we can trace out the relationship between climate and economic productivity. HDI, Human Development Index, might be a more comprehensive measure, but as far as I know, it's only measured at the national level and not, we don't have as long of a time record on it. These are statistics that are produced by the UNDP. And so it's just harder to uncover these complex relationships between climate and HDI, given these data constraints. Coincidentally, I'm working on a paper with co-authors that tries to downscale HDI to very granular level using AI. And so hopefully more studies like that allow us to have better measures, not only of climate impacts, but also of dimensions of human well-being will help us be able to trace out these studies, these relationships in higher levels of detail.
So would you like to continue answering questions because you still have quite a few, or would you like to continue and go back to questions at the end?
Let me do a couple of these examples, and I think they'll probably bring up more questions, and then we can circle back to questions at the end. So I'm going to do a deep dive into, I might make it through 4, I might only make it through 3, but a few tools across different sectors that researchers and practitioners have come up with to improve our understanding of the impacts of climate change and our ability to respond to it. So the first is called Climate Alpha. This is a kind of marketed as real estate strategies that are informed by climate risk. And so for each of these examples, I'm going to start by outlining the challenge. And the challenge here is that the combination of the physical risks of climate change and the economic transition that we expect to be spurred by climate action, meaning regulation to deal with climate change, have created a significant risk in the United States and elsewhere globally of mispricing real estate. And this really matters for investment decisions. So let me just provide a little bit more background on what I mean by physical risks and economic transition risks. Here, a physical risk from the climate to real estate is kind of the risk of natural disasters that are caused by climate change, for example, floods, sea level rise, or wildfires. These types of increases in physical risks are expected to increase damages under climate change to properties. Those damages will increase insurance costs, they'll increase the cost of maintaining and owning properties. And so a property that was previously kind of attractive from an investment perspective might become less attractive if you were able to price in the risk to that property from natural disasters spurred by climate change. There is some new research that looks at these physical risks and basically tries to estimate where properties are overvalued based on their current market value relative to what they should be if you were taking these climate risks into full account. And you can see patterns like you would expect where coastal properties, like those in California coastline, southern Florida, tend to be very overvalued because the current real estate market is not paying attention to the fact that these properties are expected to see much higher increases from natural disasters under climate change. And when you buy a property, it's not a decision over how much the property is worth today. We're thinking of really long-term investments, say over a 30-year mortgage. The second type of risk that's mispriced in real estate is something called transition risk. So imagine that there are changes to the economy that are spurred by climate change because regulators like the government and consumers are responding to climate change. So just to fix this idea, imagine that you have a carbon-intensive industry like a coal mine that sees increased operating costs under climate change because we see stricter regulations that make it more expensive to produce energy via coal. This sector is also going to become unattractive to investors who have made climate commitments. And so what we're going to see is a decline in this sector, and the local economy is going to suffer as less people are employed in, say, coal mining. You can imagine that coal towns now become less attractive to real estate investors because there's fewer jobs there, there's less demand to live there. So that's going to lower the value of properties located in these areas that really rely on carbon-intensive industries. This type of risk is also not being priced into real estate currently. So Climate Alpha is a startup company that tries to price these two types of risk, climate risk and economic transition risk, into real estate. And the way that they do this is they're combining data from multiple different sources, for example, socioeconomic data sets, market indicators, and climate scenarios, to generate forecasts of land and property values that actually price in these two different types of climate risk. And importantly, these models are designed to account for probabilistic changes in climate risk in combination with human behavior. So not just the physical risks, but also the economy's reaction to regulation. And so the target for this type of solution is real estate investors and home buyers. So big picture, the goal of this AI system is to be able to answer questions like, how are cities adapting and investing in infrastructure to protect against climate impacts? Where are jobs growing? Where are people moving now in relation to extreme heat or wildfires or sea level rise? So being able to understand these factors allows us to price climate risk into real estate projections. Specifically, how they're doing this is they're trying to create risk-adjusted valuations of land and property under different climate scenarios with the flexibility to allow the user to actually define their climate scenario. So you could decide whether you think it's likely that we're going to have a very low emissions pathway with fewer climate impacts or a very higher emissions pathway with high climate impacts. But either way, you're going to get out a valuation of your property that's adjusted for the climate risk so that you can know that when making investment decisions. In particular, how they implement this is they're combining over 1,500 data sets on climate, socioeconomic variables, real estate, and many more. They're integrating property-specific data from assessment records. So this is kind of the county office that holds your tax records for your property. And they're using a scenario forecaster that relies on convolutional neural networks. So this is one example of how this AI system is able to ingest many different data sets, understand the complex interactions between factors that price climate risk, and spit out something that a user can actually understand, which is the value of their property based on different climate scenarios. This is kind of just a schematic of how it's doing this, but essentially there's a lot of AI that's happening behind the scenes, and then the user sees kind of a user-friendly interface that allows them to visualize these projections and which are hopefully going to inform decision-making. Okay, questions on that application?
On that specific application, I don't think so. We do have on social cost of carbon and food production. But,
let's save those for the end, and we'll kind of do the other kind of closer examples. So this is one I think is really cool. We talked a little bit about being able to anticipate food crises. This is a recently published paper, I believe it came out just this year, that tries to predict food crises using news streams, and it was published in Science Advances. So just a refresher, the challenge here is that climate change is expected to worsen global food insecurity, but it's very difficult to predict when and where food crises will occur with current data and methods. This is already a problem. Severe hunger affects more than 350 million people around the globe. But the hope here is that if we're able to better respond to food crises before they become super problematic, that it will reduce loss of human life and humanitarian costs. Fortunately, this is an area where the risk factors for food insecurity are pretty well established. We have a good idea that food crises break out as a kind of consequence of bad weather, of pest outbreaks, of conflict, and of massive human migration. But unfortunately, data on these measures is often unavailable or very outdated, which limits our ability to make accurate predictions of when food crises will occur. So the paper that I'm going to preview today tries to take deep learning in combination with natural language processing to extract anticipatory signals of food insecurity from news articles. So the intuition here is that the risk factors I just described, for example, issues with weather or pest outbreaks, are often mentioned in news articles, and this is often before they're measurable in traditional data sources. News articles are published on a daily basis, and so if we're able to accurately parse and ingest these data, we could, in principle, have very high-frequency forecasts of food insecurity. So in particular, what these guys do is they start with text features that are related to food insecurity. And they choose 13 key seed phrases that are semantically close to food insecurity. So one example of a phrase would be famine. That's very highly related to food insecurity. Then they're going to use a text parser to extract semantic causes of food insecurity. So for example, in the sentence here, which is extracted from a real news article, famine is the key phrase, and it says famine may return to some parts of the country where floods and pests have ravaged crops. So the parser would extract the words floods and pests as causes of famine. Now they do this using a giant body of text, and this enables them to uncover a number of phrases that are highly associated with food insecurity, and they're able to classify these into different clusters. So here you can see examples of these phrases. For example, terrorism in red is part of the conflict and violence cluster. Flee is part of the food displacement cluster. And I don't know, climate change is part of the environmental issue cluster. And so this is going to allow them to identify words that when they see in text might be predictive of coming food insecurity. Then what they do is they validate these phrases that parser came up with against traditional risk factors for food insecurity. So this just means that they're looking at the correlation in the mentions of that phrase, for example, conflict, with the traditional predictor of food insecurity, which might be something like a conflict fatality account. And across many of these phrases, they find very high correlations with traditional predictors of food insecurity that, again, do a really good job of predicting food insecurity, but are hard to use in predictive models because there's very poor data on these in many developing countries, or where there is data, it's often outdated in a way that makes it useless for predicting future food insecurity. So now that they've established that these news phrases are highly correlated with the traditional data sets that are used to predict food insecurity, they run a number of different models to be able to predict food crises. And so here they're using data on past food crises, and they're essentially saying, if we use different models, how good of a job do we do of anticipating that crisis before it occurs in the data? So they have kind of 6 different models here. The first, which they'll call traditional, is in light blue and is used to predict food insecurity using those traditional risk factors associated with food insecurity for which data is often unavailable or outdated. The second, in the darker blue, combines those traditional risk factors with expert opinion, which is available in a more timely manner, and they get a modest productivity boost. Here you're saying precision versus recall. So the further out this curve moves, the better for accuracy of predicting food insecurity. Then they use their news model. So that's in yellow here, which is how well do you do when predicting food insecurity using these phrases extracted from daily news articles? They show a modest boost of combining that with expert opinion. And then the best performing models in this pink and red are actually from combining traditional models, which have these very well-established predictors of food insecurity, but that might be outdated, with the news models, which use this high-frequency information that you can parse from daily news articles. And so when we use these combined models, we get these precision versus recall curves out here in pink that do a very good job of anticipating food crises. So let's dig a little bit under the hood here. Here you're seeing this for 3 different food crises outbreaks, how well of a job the model does at actually anticipating this outbreak. So let's look first at the first column, which is a food crisis that happened in Somalia in 2010 and 2011. The IPC phase is kind of the official measure of food insecurity. And when this jumps up around June 2011, from a level 2 to a level 4, that's when we have the food crisis outbreak that's highlighted by orange here, by this orange rectangle. So if the authors had just used the traditional model here, they would have gotten the prediction in this kind of teal color of no detectable food crises. But when they use the traditional model plus their news model in pink, they're actually able to very closely track the food crises and to anticipate this before it becomes a crisis. And in order to see kind of the mechanism here, on the top, they're actually plotting the mentions of conflict and violence in the news that's really leading to this prediction of a food crisis. And we can see that these mentions ramp up in the months before the crisis. So we can actually get an idea that this crisis is coming so that we can deploy aid before it becomes too big of a problem. You can see similar patterns here in Southern Sudan and in Ethiopia for different food crises, where using this information on daily news mentions of risk factors for food insecurity allows us to accurately predict the food crisis before it occurs in a context where a traditional model wouldn't have allowed for that anticipation. Okay, are there questions on that application?
No.
Okay, great. All right, so another example that I think is really cool is using AI to forecast floods and issue early warnings. There are many different companies that are doing this now. I'm going to focus on one of the larger scale ones, which is an effort by Google. This is an end-to-end effort that attempts to anticipate floods, produce detailed risk maps, and then send out early warning signals through your Samsung phone. So the challenge here is that climate change is expected to increase flood risk worldwide, but many of the most vulnerable communities lack operational early warning systems that would allow them to anticipate and avoid the worst impacts of flooding. So just for some context, flooding is the most common and costly weather-related disaster across the globe. It's estimated that it causes thousands of deaths every year and in excess of about $30 billion annually. And unfortunately, flood risk is increasing not just because of climate change, but also because of other forcing factors such as population growth and urbanization that are increasing the amount of people and capital that are exposed to flooding. In some of the other contexts that we've discussed, floods early warning systems are really important to mitigating some of the worst impacts. They can allow for timely evacuation. They can help property owners protect against damage by making adaptive investments. But unfortunately, the UN estimates that over half the global population lacks adequate early warning systems for natural disasters like floods. And a key barrier to developing these early warning systems is lack of data in poor regions. So the goal here is to develop an ML system that can contribute to modeling flood forecasts. And again, I'm going to focus on Google's application today, but there are many other researchers and firms that are implementing ML models in this space. And essentially, they have two ways where ML can really enter into the flood forecasting pipeline. First, they can help in what's called a stage forecast model, which is essentially a model of how high rivers will get. And the second is they can help in inundation modeling, which is essentially a model that translates how high a river is into flood extent maps. And the basic idea here is that ML, such as deep learning models, can provide improvements over traditional models in both accuracy, but also scalability of these models to regions that have poor data inputs. So Google's program, which we'll focus on today, was first developed in India in 2008, but now it's active in over 15 countries across Africa, South Asia, and Latin America. And it's already issued over 15 million alerts for floods. So like I described in the beginning, this is really an end-to-end system. So it starts with data ingestion, then it does that stage forecast model, how high a river is going to get. It translates that into an inundation map. And finally, it issues alerts to users through their smartphones. Okay, so the stage forecasting model, they have two different types here. One is simpler, which requires less inputs and is more interpretable. The other one is a little bit fancier. So the simple one is just a simple linear regression where they're inputting the past stage of the river. Again, stage is just how high the water is above some arbitrary reference level. And it's going to output predictions of future stage or river height. The second, more complicated model uses long short-term memory or LSTM networks, which is essentially a recurrent neural network that learns input-output dependencies. The basic idea here kind of follows from the linear regression, where the model is taking into account past river levels, both at the stream gauge that you're monitoring and at upstream gauges, and outputting a prediction of future river levels. These river level models can then be translated into inundation maps. They use two types of models with Google. One is a threshold model, which gives you flood extent only. So you can think of this as a binary map of whether or not your location is flooded. The more complex one is a manifold model that takes into account something called a digital elevation map, or a DEM, and actually allows them to project flood depth. So they can tell you not only whether your location is flooded, but the severity of the flood at your location. And then ultimately, these alerts are sent out to the public using their smartphones. And like many other AI applications here, there's an emphasis on increasing interpretability by the user. So for example, they might give you flood depth with a little diagram of how high that might come up on a human. The punchline behind this system is that this allows for flood forecasting on a very high frequency basis, so they can issue warnings, and in areas that have traditionally poor monitoring, because all they need to know is an elevation map. These are available globally, and river stage models, which is pretty well monitored, even in low-income countries. Any questions on that application?
We do have one on famine, if you want to circle back.
Sure.
So for the Bella Shankar et al. Case study on NLP-based famine prediction, does the model also predict the causes of the famine?
So not explicitly. What it does is it uses this parser to extract what appear to be causes based on semantics in the news articles. So I think this example is kind of the best way to understand it, which is by understanding sentence structure and kind of the causal relationship between words within a sentence, the model is able to extract causes of famine based on how the person wrote the news article. Causal relationship is kind of a tricky word here, because this isn't necessarily causal in the statistical sense. It's just causal in the sense that the person who wrote this news article is attributing the famine to these phrases.
Thank you.
Okay. I'm going to move on to the last application, which is an AI system for targeting biodiversity conservation. This might have been covered in an earlier lecture, but one kind of big problem posed by climate change is that it's putting enormous pressure on the world's last remaining ecosystems and the species that they contain. And so we're worried about big changes in biodiversity as a result of climate change. Protecting biodiversity is costly economically because it means that we have to restrict growth in other sectors, for example, in urbanization or in economic output. And so it's really important to be able to target biodiversity investments in a way that maximizes species protection and that minimizes economic impacts. And so the technology I'll be showing you today is one framework for thinking about how to make trade-offs between those two things. The tool is called Captain. And it's basically an AI tool for systematic conservation planning that optimizes conservation policy while monitoring resource constraints, such as a limited financial budget. And so essentially what this tool is going to do is it's going to take into account a wide array of factors, both factors related to biodiversity, such as species richness, but also factors related to the economic cost of conserving areas, such as population density or the value of land resources. And it's going to feed these into a model that allows the user to make trade-offs between competing objectives. And so when I said that AI could be really nice for optimizing when you have multiple objectives, I think this is kind of a nice example of how this could play out in practice, which is there's trade-offs inherent in protecting any given area for biodiversity conservation. And these trade-offs include maximizing, say, for example, species richness while minimizing economic cost, or maximizing protected area while minimizing impacts on phylogenetic biodiversity. What this model does is it allows us to basically trace out the frontier of what's optimal along multiple dimensions. And there's not just one solution to this problem. It's really up to the user or the regulator to decide which dimensions are important to them. So if I'm a user that puts more weight on minimizing damages to the economy, I might choose this polygon here, which is on the optimal frontier, but puts more weight on minimizing economic damages. Whereas conversely, if I'm a regulator who's really interested in maximizing protected area, I might choose this frontier here on the right, which is equally kind of optimal along multiple dimensions, but is optimizing protected area relative to these other considerations. So this is just an example of how AI can help when you have multiple objectives and you need to trace out the optimal frontier across those objectives. Then, of course, there's still more than one solution, and it's up to the user to decide what's more important to them and what's less important to them. Oops. Okay, so I realized that was a lot to cover in an hour and a half, and I want to open up the rest of our time for questions or kind of thoughts from the audience on what would be helpful to hear more about.
First of all, Hannah, thank you so much for this very interesting lecture. Now we'll go back to the questions. Is social cost of carbon the same among countries? If not, how do we account for the differences?
Yeah, so that's a good question. The policy right now in the United States is to use something called a global social cost of carbon, which basically takes into account all of the damages across the whole globe from emitting 1 ton of carbon dioxide. There has been some debate, and under different presidential administrations, we've used a US-specific social cost of carbon, which only takes into account damages caused to US citizens from that ton of emitted carbon dioxide. Like you saw on the kind of maps at the beginning of the lecture, the impacts of climate change are very different across the globe. They're actually beneficial in some areas, very harmful in others. And so you can imagine a social cost of carbon specific to each country, one that's global. You could also imagine a social cost of carbon that takes into account welfare of country in different ways. So in the extreme, you could count everyone across the globe equally. In another extreme that the Trump administration used, you could give everyone in the United States a weight of 1 and everyone else in the world a weight of 0. But you could imagine a country putting differential weights somewhere between 1 and 0 on their own population versus other populations. You could also imagine upweighting damages to kind of more vulnerable populations where the damages are a larger % of their income, for example. Things like that. So there's a lot of debate on how to actually construct this, especially as you get more granular estimates of who is damaged more by changes in the climate.
Yes, that's a really interesting topic. We can go back to it afterwards, but now we'll go to the next question. So reducing food waste seems like low-hanging fruit in terms of reducing hunger and ultimately human suffering. But this still hasn't been solved. Could you provide more insights on what are the hurdles we still face, either from a policy, economic, or technological perspective, to overcome this and better redistribute food that's not consumed?
Yeah, so I agree. It seems like low-hanging fruit. It seems like we're leaving something on the table here. And I think that this is a solution that is low-hanging fruit in the sense that it's actually in the companies who are producing and transporting food's best interest to reduce waste because they're losing profits too. So this is an area where actually the economic incentives and the social priorities are actually very well aligned. So it seems like an area we should be able to make progress. Why is it hard? One, infrastructure just limits our ability to transport food around the globe. We're really bad at projecting demand for food. Even within a households, people are very bad at understanding how much food that they're going to use in a given waste. And so a lot of food goes to waste in your refrigerator. Again, this is somewhere where making better decisions would not only help the environment and kind of global food security, but would actually help your individual wallet. So it seems like somewhere people should be focusing their attention. But for some reason, it's just really either hard to predict how much food you're going to consume, and that's at an individual level, at a store level, at a national level. And the infrastructure limits our ability to actually transport food to where it's needed most. I think this is why folks are so excited about AI in this space, is that being able to predict demand and being able to optimize shipments in a way that takes advantage of the infrastructure that we do have is something that AI is really well suited to. And there's clearly, a lot of opportunity here for making progress. And so hopefully you saw some of this in the transportation lecture, but there's kind of new models that are being brought to bear on how to transport goods efficiently that could be really helpful here. And there's new models on how to predict sales at the store level that could be really helpful for making sure that food doesn't go to waste on the shelf. And hopefully as kind of planning technology becomes better at the individual level, there's also going to be kind of apps or other AI interfaces that allow us to better predict at a household level how much food we need so that we're not over purchasing and under consuming.
Thank you. Thank you for that reply. We have a question about the capital model. So thank you for covering the trade-offs between conservation and human expansion. Do you have any idea what's happened to the capital model since it was released? For example, is it a tool that started to be used by certain policymakers or governments, or has it been developed into an enterprise product? Could you shed some light on this process, how it works from models developed in a lab or research institution to tools that are used by policymakers?
Yeah, so I'm not exactly sure what the state of Captain is right now. I know that it's publicly available online. You can go to their website, and their goal is to get this used by decision makers. And so I think there has been some effort to engage with policymakers on distributing this tool. I can speak a little bit in general to what happens from tools developed by researchers, and those can take a number of different paths. Increasingly, I think researchers are putting these tools out in the public domain, kind of open source code, open source data to increase their impact for social good. However, there are also research teams that patent to these technologies and sell them. That's not a bad thing. Being able to sell these technologies is actually incentive to produce more technologies that can help improve human welfare. So not knocking that by any means. And some researchers even create kind of spin-off companies. I think that's how Climate Alpha was started, that are for-profit companies that came out of kind of academic research agenda. So there's many different ways that these things can move forward, each of which have pros and cons. But the important thing is that they get into the public domain and are actually reaching decision makers. And I think that's becoming more and more common as we've seen kind of a push in this sphere to make these methods more transparent and more accessible.
Thank you. So if you could, still on part 2 about the models, I wanted to ask you about the risks of manipulation of these models. So, for example, you mentioned Google tool, and it made me think about how people can manipulate, for example, Waze, so that their street has less noise, or the road they usually take has less people in it, and they feed false information, saying there are a lot of cars in that particular street. So that's just one example, and I was wondering if people tampering with the inputs they give to these models could alter the results of the models you have shown us.
Yeah, I think that is always a risk with AI. I mean, the one that comes to mind for me is the text analysis one for predicting food insecurity. You could imagine a government that had lots of control over the media could manipulate the types of words that showed up, and that would show up in downstream predictions of food insecurity. I mean, this assumes that bad actors, are very sophisticated and that they have an incentive to manipulate these models. I think one of the nice things about AI is being able to ingest predictors from many different data sets and dimensions, some of which might be easier to manipulate, some of which might be harder, but not relying on only a few metrics can hopefully make the models more robust to being manipulated in that way, if it's harder for users to manipulate all of the things that matter. I think ethics in AI is a big topic, luckily receiving a lot of attention, and it's up to the data producers and users to try and build in systems that reduce the possibility for that type of manipulation. But of course, it's not always possible. This isn't a problem that's unique to AI. This is kind of endemic to any sort of system that we're using that matters for social and economic outcomes. But yeah, I don't know. Important topic. Hard to say just how manipulatable these things are.
Thank you. Also, about the social cost of carbon, I also wanted to ask you, are you familiar with the Ford Pinto case from the 70s? The graph that you showed made me think of that case that's very famous in law schools, about making a choice based solely on cost, and really doing the math of what's going to cost you more, and choosing just to choose the path that it will cost you less, regardless of other consequences. So while attributing the value of future generations, the graph that you showed at the beginning, you can attribute a value to it. Could you please go back to that subject into a little bit more detail, and perhaps explain to us what sorts of factors go into that kind of calculation from an economic perspective?
Yeah, so I'm not familiar with the case, so please correct me if I go off course here. But I think, the idea isn't to make the decision based on the economic cost alone. It's basically understanding that there's a trade-off between curbing emissions, which reduces damages from climate change, and allowing emissions, which increases well-being in other ways by, for example, contributing to economic growth and comfort that increases human well-being. And we need some way of being able to balance those costs and benefits that's not completely arbitrary. And so that's where the social cost of carbon comes in. The measure as it stands right now is based mainly on income, which is a very incomplete dimension of human well-being. But there's a lot of effort in this literature to get other dimensions of human well-being into the social cost of carbon, so that it's not just based on dollar signs, it's also based on things that we can't necessarily measure in dollar signs. Now, the caveat is that all of those things have to be converted back into dollar signs to actually use this framework of decision making. But it's not like they're left out, it's just that they are converted into dollar signs so that they can enter into this cost benefit decision. I don't know if that got at your question.
Yeah, thank you. Just out of curiosity, the Ford Pinto case is when there was a bad design in a car in the 70s, and the company knew that it could result in accidents. and they calculated the legal risk of the lawsuits, and it was cheaper to pay the damages than to recall the cars. So that's why it's a famous case of a choice being made and a calculation being made, and the choice being made strictly by the numbers. And seeing the graph, it came to me that it was probably something important to keep in mind while attributing value, to be very careful not to make that sort of decision.
Yes, this is a really great point, because if it was the same person, right, that was paying the cost of the car recall and that was experiencing the damages, you wouldn't have this problem. The problem is that it's a different person that's that's experiencing the damages than the person that's making the profit. And this is central to the social cost of carbon too, which is the people that are benefiting from the emissions are not the same people that are hurt most by climate damages. And that's why the social cost of carbon is kind of useful as a summary statistic at a global level to understand how much mitigation we need to be doing, but it doesn't solve the problem of climate change having inequitable consequences. That needs to be handled separately through other policies that say do redistribution if you wanted to make everyone whole again. Hence some of the tools that are trying to understand how you can attribute damages to specific polluters. In an extreme case, you would be able to use those to facilitate financial transfers, although I don't think any of us think that that's going to happen politically anytime soon.
Thank you. We have another question. Are there efforts being made to standardize methods to build these models to make it easier to bridge the gap for low resource countries to develop policies to suit their particular situation?
Yeah, there are. And I think this is kind of one of the cool areas, is that these models were originally just a researcher made assumptions and gave you a number. And increasingly now they allow for flexibility for decision makers to actually enter their own assumptions and their own priorities and get out a number that reflects those. I, before joining Caltech, worked at a place called Resources for the Future. That's a nonprofit that does environmental economics and policy analysis. And they had a big effort on the social cost of carbon, estimating what it is, but also developing a toolkit that allows decision makers to engage with the different pricing schemes. And so that's on their website. That's one example that I know well, but this is something that's becoming increasingly widespread to make these kind of estimates more capable of being tailored to individuals' needs.
Thank you. Well, we have a question about the human aspect. So how do you think AI can predict human economic decisions or perceptions regarding climate change? Because people are difficult to predict, as human behavior is not an exact science.
Yeah, so this is really hard. This is, I think, a cool area of research, and we're seeing all different types of big data sets being combined with AI to understand behavioral responses. Let me give two examples here that I think are particularly interesting. One example is people look at human mobility patterns. So if you bring your phone with you somewhere, it tracks your location. Researchers get that location data from mobile providers, and they're able to actually see how people change their location responses in response to climate. So if it's a particularly hot day, do I stay in my house? Do I go to the library instead of going to the park? And when you add up all of these little decisions, we're able to see how people are responding to changes in their climate and how they spend their time, both work time and leisure time. Another interesting example is understanding how people change their purchasing behavior. So many stores will provide their scanner data to researchers. So every time you purchase something at the store, they scan it when you check out. And then all of that data on exactly what people bought when is sent to some researcher somewhere, and they're able to untangle patterns in what people are buying based on what weather they're experiencing or what weather they expect to experience based on the forecast. And so, for example, we can see that before a hurricane, people go out and they buy a bunch of toilet paper and water bottles. That's an extreme scenario, but we can also see that maybe people buy fans when there's a heat wave coming. And this allows us to understand to what extent people are adapting to these climate shocks by making investments in things that could mitigate some of their negative impacts.
Yeah, that's really interesting. Thank you for the reply. So I also wanted to ask you if you want to get into more some more economical aspects. So I don't know if you want to talk about what are black swans and green swans, but during your lecture, these concepts really came to mind. And what I wanted to ask you about this is, how do you think that these concepts that are very inherent to the economical area can be useful for stakeholders from, for example, computer science that are watching us right now? And how do you think these concepts could help them deal with the issues of AI in social and human systems for climate change, adaptation, and mitigation in their area? So what could they transpose from the economical area to their area? And perhaps, I don't know if you want to go into these concepts of what is a black swan and a green swan.
So you might actually have to help me out here. I don't know what a black swan and a green swan are. I don't know if you do, Amanda, or if that was a question posed by the audience.
Basically, they are very hard to predict, but not totally impossible events. So the black swan was because people thought before they got to Oceania that there were only white swans, and saying that you saw that's like a black swan is kind of like having seen a UFO or something. But then they got to Oceania and there actually were black swans. So that's an allegory to say that there are some things that are really, really hard to predict, seem almost impossible, but then they just happen. Such as, for example, the COVID pandemic was called the black swan. So the green swan would be the same thing, but with climate situations.
Yeah, so this is actually kind of central in understanding climate damages. And I think one example that's, we hear a lot about in this space is really damaging natural disasters. So these are events that are really hard to understand because we just don't have many of them in the historical record, and they're hard to predict, but we do have a good sense that this type of really damaging natural disaster could be possible in the current climate and could be even more likely in a changing climate. And so for computer scientists and people who are more steeped in AI, this is essentially like an out of sample prediction problem where we want to be able to understand the consequences of highly damaging natural disaster. In most of our literature, we try and understand damages based on past events, but what if there's no past event that looks like that, or not at the frequency that we expect in the future? And so this is a really hard prediction problem because we're trying to learn from the past about the future, but we don't have anything in the past that looks like the future. That's kind of classic out of sample. And so, the methods here are rapidly developing and are kind of not totally adequate yet, but some of the interesting things that people do is kind of create synthetic events as a combination of past events that might look more like what we expect to see in the future, but haven't seen in the historical record. So yeah, big problem. We expect most of the damages from climate change to happen from these kind of like tail events, but we're really bad at modeling those. And that's what leads to a lot of uncertainty and damages from climate change, both over the short term and the long term.
It sure is complex. So I think we are out of questions. So do you have any other remarks? We still have about 5 minutes.
No, I just want to say thank you so much to everyone for attending tonight, and thank you to the organizers for inviting me to participate in this series. I've learned a lot from the previous lectures, and it was really fun to be able to engage with this audience today. So thank you, and I'm looking forward to the next day of lectures.
We thank you. We thank you for your talk. We all learned a lot, and you inspired us to reflect in new and deeper ways on this really complex but also really fascinating subject. And thank you as well to all of those who attended. Thank you, of course, to all of the CCAI team and especially the Summer School team. And thank you again, Hannah. And also we hope to see you back here tomorrow, because tomorrow is the closing day of the Climate Change AI Summer School 2023. Tomorrow at 5:30 p.m. UTC, we'll have a session of lightning talks on some additional topics, and that will definitely be interesting. So thank you again for everyone who's watching and also everyone who is participating in the summer school for your support. And we'll see you tomorrow. And thank you again, Hannah.